When I ask you to solve this equation, there's specific answers, right? Like sine only equals 0 or 0 pi, right? But if it's an identity, it's true for no matter what angle you plug in there. So like sine squared plus cosine squared equals 1, any angle you think of works in that. So to prove that an identity is true, you can't just say, let me plug a number in and check it. You have to do like a proof, like show that it's equal to each other. And so really important that you know the difference between solve this equation, find the exact solutions, and verify that this identity is true means like write a proof. Okay, so that's what we're going to spend the next 2 weeks. So a lot of words today, and I wrote them for you because I just didn't want to have to wait for you to handwrite them all, but I cannot stress enough how much you need to make sure you're aware of what these words are saying and that you use this as a guide. Also, there's a lot of examples in your book that are different from my examples that you should look at, or if you are if you don't need to learn that way, you can look up some videos and find other examples looking at them. But the only way you're going to get better at these is to understand the rules and practice them. So this is what your book says about proof, and I'm going to give you my advice. Unlike a geometry proof, it's kind of like an equation the whole time, but like a geometry proof, you know what you're trying to prove. So it says, the proof begins with the expression on one side of an identity, and the proof ends with the expression on the other side, which means kind of like geometry. It's like, given this, prove that it equals this. So basically you're trying to prove, make one side equal the other side, okay? Step 3, the proof in between consists of showing a sequence of expressions, each one easily seen to be equivalent to its preceding expression, which means when you're writing a proof, you can't skip steps, right? Just like in geometry, you always know the end, so you would like write your given, and then you'd write the end, and then you just made up the steps in between and hope the teacher didn't notice, right? I'm on to you. The in-between is the proof. And that's the part that I have to actually check each step. And if I can't follow what you did from one step to the other, then that means your proof is missing something. So it's always better to show more steps than less steps in a proof. Alright? And I have another way. We're going to do kind of one together to kind of show you the idea. And then I'm going to give you my list of strategies that I've kind of come up with over the years. We have to work with one side or the other. This is not an equation that we're solving, which means never can you add or subtract something to both sides, or can you square both sides, because this is not really the equal sign that we're used to. It's kind of like saying, prove that this equals this. So I'm going to pick one side to work with. I'm going to pick this side, and I'm going to turn it into this side, just using what I know about algebra and trig identities. So somehow I have to figure out how to change addition into multiplication. That's exciting, right? Anybody have a suggestion? Write it in terms of sine and cosine sounds like a great choice, because secant and cosecant could also be written in sine and cosine. So over here, I'm not going to number my steps like in a proof from geometry, but I'm going to write them very sequential, which means each line should be a proof, like a step in your proof, right? So I'm just going to write this as sine over cosine plus cosine over sine. And to keep kind of things in order, I'm going to always rewrite this other side and say that's going to equal secant x cosecant x. And this side, right, look at what's over here to kind of try to help you see what you should do. Hopefully. Always a good strategy now that if I have fractions, what do you think I should do if I have two fractions added? Common denominator. And again, each one easily seen means that, like me, being a math person, I'm going to be able to see what you're doing here. So if you get a common denominator in your next step, you have written as cosine x times sine x. I'm going to be able to see, oh, they got a common denominator, so you don't have to, like, duplicate my steps here. This is really important, right? This is what we've been working on this week. This side has cosine, but it doesn't have sine, so that means I need to multiply sine over here, which would give me sine squared plus This side already had sine, but it doesn't have cosine. So with that, means cosine squared. Sometimes you do some stuff in a proof, and it doesn't look like you're getting any closer, right? You don't see what's happening. Sometimes you just gotta persevere and keep going. And sometimes you might decide this is not a good strategy, and I'm gonna start over and maybe try a different route. So you always kind of hope that you can either see something to simplify, or you can see, hey, I'm getting closer to what I need on the other side. I'm pretty excited about this because I look at the top of this, and what do I know that sine squared plus cosine squared equals? 1. So I'm going to write that as 1 over cosine x. And then remember, this is what we're trying to get. Are we about there? 1, I now have multiplication and not addition, so that's good. And if I have cosine times sine in the bottom of a fraction, do I have this? Yeah, because cosine you can bring up and make secant, and sine you can bring up and make cosecant. And so your last step should always be showing that they're equal to each other. So my last step is going to say secant x times cosecant x equals secant x times cosecant x. And I like to put a little check mark to feel like I accomplished something. We don't have to check mark. Sometimes we forget. We do this when we get proof by induction. That's some fancy proven thing. I could just put a stat basis. That's exciting, right? What's hard about proofs? The same thing that's hard about day 1 of 5-1. I can't tell you every time where to start, right? I can tell you that sometimes I start and I get nowhere, and I just have to start over and I can't tell you if you don't know your rules of algebra, you're going to really struggle with making sense of But practicing, and the more you practice, the better you get at them, because you just have to kind of build those skills. So, to try to help you with that, very bold fonts here, I put some tricks. It's not really tricks, they should say tips, but they're not really magic tricks. The things you should be aware of. If you get stuck, look back at this and see how I tried all this. So, step 1, work with one side at a time. Usually the side that looks more complicated, because it means you're going to have more to do. Get a common denominator, factor something out. Lots of different things you can do there. Remember, it's not an equation, so you can never like move something over to the other side, right? It's like two separate sides going on. Look for all those strategies that we built in 5-1. Can I factor? Can I add fractions? Can I square a binomial? Can I get a common denominator? Those fundamental identities, especially the Pythagorean identities, see if you could use those. Look at what you're trying to prove, right? If what you're trying to prove has tangent and cotangent in it, see if there's some way you can change what you have on this side into tangent and cotangent. Remember which pairs of your Pythagorean identities match up, right? Cotangent squared and cosecant squared, sine squared and cosine squared. Algebra, right? Recognizing that you can factor a perfect square minus a perfect square. And something that can always be tried, sometimes it makes a mess, but you can always change everything in terms of sine and cosine and attempt something there. Always try something. Like I said on All About 5-1, if you just come in with a blank sheet of paper and said, I didn't know how to do any of my homework, you're never going to get better at it if you're not trying them. And I can show you my papers of where I don't erase, because I always think that maybe it was the right thing and I don't want to erase what I did. But if I try something and it doesn't seem to be working, either over next to it I start over, or underneath it I start over, and then maybe I'll end up going back to what I started with. But you just have to keep trying things if one thing doesn't work, okay? So let's practice a few more. We'll practice some easier ones. Not all proofs have to be really complicated. They could just be 1 or 2 steps. So verify the identity. We want to show that these two sides are equal. So you want to pick the side that's more complex to work with, right? Like, I'm not going to pick to work with 1. I'm going to work with this side and try to make it equal 1. There's more than one right way to do this. there's definitely wrong ways to do this. Like if you break that rule or you say something equals something that's not true, that's not okay to do. But not everyone's going to always do this correctly. So you want to just kind of look at it and say, what could I do here to simplify this? Any suggestions? Right? If you see a Pythagorean identity or a form of a Pythagorean identity, you can substitute that in, and that is, if you don't just show me the work there, right? 1 plus tangent squared equals secant squared. So Lois says that you can just replace that with secant squared, and that's a true statement. Pythagorean identity says 1 plus tangent squared equals secant squared. So if you subtract 1 over here, we're just doing substitution. We're saying that secant squared minus 1 equals tangent squared. So we're replacing all of that with what it equals. Pretty much there, right? Maybe you just want to say it equals 1, but I'm going to show you. I'm going to say cotangent is 1 over tangent. Proof and show that lots of other options there. You could have changed the sine and cosine so they cross out. You could have changed tangent to 1 over cotangent. Make it show me how when you show that they equal each other and number 3, I think, is a good example that you could work with either side of this and make it equal the other side. And there's no wrong way to do that on here. If you choose to work with tangent squared plus 4 and turn it into secant squared plus 3, that's right. If you choose to work with secant squared plus 3 and turn this side into that, as long as you prove that one side equals the other, you're allowed to do that. I'm going to actually do both just so I can show you. I think we're using the same identity up here, though. Do you agree with that? Real quick, what's not okay to do here is to subtract 3 over here. Follow me on that? It's not an equation, so you cannot subtract 3 and then be like tangent squared plus 1 equals secant. That's true, but that's not what that equal sign means, right? So just make sure that we're not treating it like that. But if I know 1 plus tangent squared equals secant squared, if I chose to work on this side, could I replace this secant squared with 1 plus tangent squared? And I would get 1 plus tangent squared plus 3. Right? And that's true. You just add them up now. You get tangent squared theta plus 4 equals tangent squared theta plus 4. If I chose to work with this side, tangent squared is going to equal secant squared minus 1. So you get secant squared minus 1 plus 4 equals secant squared plus 3. And again, I'm just combining those, and I get secant squared plus 3 equals secant squared plus 3. So I just want to pick this example, not that it's a hard example, but just to show you that you're allowed to work with whichever side you see something to work with. What takes me forever to grade these on a quiz or a test, but also part of the reason I like this chapter is because it really makes me think, because I can't be out and everyone has the same thing. I have to really look at your stuff, and sometimes you find ways to do a proof that I would have never thought of doing. Sometimes it's way more steps than mine, and sometimes it's way shorter steps than mine. And I think, oh, I never thought of it that way. So what makes it our chapter, and I think what makes it kind of, the math always has one right answer. Not really. Like, we all end the same way, but the steps to get there can be different. You also have some questions, right? In one of this, that they ask you, make sure you read the correction. It says, decide whether or not this could be an identity for sine of x. Right? I wish they would have worded this a little better, But basically, they're saying, does tangent x over secant x, question mark, does that equal sine x? So basically, some of these are going to have an answer of no, because they're asking you to kind of see, is that true? When the directions they verify this identity, it will always work. They're not going to give you the work. But today they're just trying to show you that not everything is going to be. And so you're going to do this the same way you would do a regular proof, but you just might say no on it doesn't work. So this is kind of like what Mackenzie was just asking about earlier, like what would I do on this? Lots of options. But for me, if I see a trig function in the bottom and there's no addition with it, the first thing that I would do is I would bring it up. Because secant in the bottom of a fraction is the same as cosine. So instead of dealing with like a complex fraction, I like to bring it up. You have to do it that way. And then tangent is sine over cosine. And that is going to work, right? So I get sine x equals x. So since that's true, is this an identity? I'm going to say yes. Obviously, you have to have some evidence to support your yes or no answer on this. So those are meant to be like starchy out flow sensors. So those are the first couple on your homework. Are that. Questions? What about this? Which side would you choose to work with on this? I would definitely choose this side because there's parentheses I could distribute. It's not wrong again if you choose to work here, but I think you always want to choose the more complex side. So I'm going to give you a head start on this. Not that I'm expecting you to get all the way there the first time, but at least distribute and maybe think about, you know, could I change it to sines and cosines, or do I see anything that cancels, and see if you can get partway there before I just do it for you. So this is multiplication, so the cosine is just going to go with all of this, right? So that would become cosine sine. So you just distribute it to each term. I distributed, and then I change of sines and cosines, which is a good choice, especially because over here is just sine and cosine. So again, you have to know those identities, that tangent is sine over cosine, cotangent is cosine over sine. And that just cancels out. So I get sine. Then over here, the sine cancel out, the cosine times cosine, which is cosine squared. Okay, so the homework, the first 3, 5, 7, and 10, those are the ones that just ask you, does it equal sine of x? Which means that you might say no on some of those, right? They might not work. But then after number 10, they say prove the identity. Some are going to be easier than others. Some are going to be tough. I expect that this is going to be a tough homework assignment. I expect that you're going to come in on Monday with some other questions. But what I expect is that you try it and that you jump around. You get stuck on 12 and 15. Don't not even try the other ones, right? Because some of the end you might actually get more than the other one. And we'll go first. We will definitely have a quiz Monday next week, like a real life quiz, not a homework quiz. A quiz over this, and we'll have a week or two the next week, so we will have one, so just have to keep that in mind if you have put off you actually have to kind of work, please use that time wisely, so that you can because like 1 over 10